Hi, so for today's video, we will be discussing about digital systems technology and embedded systems. Digital technology is a base to process. Digitalized information is recorded in binary code of combinations of the digits 0 and 1, also called bits, which represents words and images. Digital technology enables immense amount of information to be compressed on small storage devices that can be easily preserved and transported. Digitalization also quickens data transmission speeds. Digital technology has transformed how people communicate, learn, and work. An example of a digital system is a computer. A computer manipulates information in digital or more precisely binary form. A binary number has two discrete values, 0 or 1. Which of these discrete values is represented by the off and on status of an electronic switch called a transistor? All computers therefore only understand binary numbers. Any decimal number with 10 digits from 0 to 9 can be represented by a binary number with base 2 with digits 0 and 1. The basic block of a computer are the central processing unit or CPU, the memory, and the input-output. The CPU of the computer is basically the same as the brain of a human. A computer memory is conceptually similar to human memory. A question asked to a computer is analogous to entering a program into the computer using an input device, such as the keyboard. And answering the question by the human is similar in concept to outputting the result required by the program to a computer output device, such as the printer. The main difference is that human beings can think independently, whereas computers can only answer questions that they are programmed. An increasing majority of applications in electronics, as well as in most other technologies, use digital techniques to perform operations that were once performed using analog methods. Here are chief reasons for the shift to digital technology. Number 1. Digital systems are generally easier to design. The circuits used in digital systems are switching circuits, where exact values of voltage or current are not important, only the range in which they fall. Number 2. Information storage is easy. This is accomplished by special devices and circuits that can latch onto digital information and hold it for as long as necessary. And mass storage techniques that can store billions of bits of information in a relatively small physical space. Analog storage capabilities are, by contrast, extremely limited. Number 3. Accuracy and precision are easier to maintain throughout the system. Once a signal is digitalized, the information it contains does not deteriorate as it is processed. In analog systems, the voltage and current signals tend to be distorted by the effects of temperature, humidity, and component tolerance variations in the circuit that processes the signal. Number 4. Operation can be programmed. It is fairly easy to design digital systems whose operation is controlled by a set of stored instructions called a program. Analog systems can also be programmed, but the variety and the complexity of the available operations are severely limited. Number 5. Digital circuits are less affected by noise. Spurious fluctuations in voltage are not as critical in digital systems because the exact value of a voltage is not important, as long as the noise is not large enough to prevent us from distinguishing a high and low. Number 6. More digital circuitry can be fabricated on IC chips. It is true that an analog circuitry has also benefited from the tremendous development of IC technology, but its relative complexity and its use of devices and cannot be economically integrated have prevented analog systems from achieving the same high degree of integration. Moving on to our next topic are embedded systems. An embedded system is a combination of computer hardware and software, either fixed in capability or programmable, designed for a specific function or functions within a larger system. Industrial machines, agricultural and process industry services, and devices, automobiles, medical equipment, cameras, household appliances, airplanes, vending machines, and toys, as well as mobile devices, are possible locations for an embedded system. Embedded systems are computing systems, but they can range from having no user interface, for example, on devices in which the system is designed to perform a single task, to complex graphical user interfaces such as in mobile devices. User interfaces can include buttons, LEDs, touchscreen, sensing, and more. Some systems use remote user interface as well. Here are quick facts about the history of embedded systems. So, embedded systems date back to the 1960s. Charles Stark Draper developed an integrated circuit, or IC, in 1961 to reduce the size and weight of the Apollo guidance computer. The digital system installed in the Apollo command module and lunar module. The first computer to use ICs, it helped astronauts collect real-time flight data. In 1965, Autonetics, now a part of Boeing, developed the D-17B, the computer used in the Minuteman I missiles guide system. It is widely recognized as the first mass-produced embedded system. When the Minuteman II went into production in 1966, the D-17B was replaced with the NS-17 missile guidance system, now for its high volume use of integrated circuits. In 1968, the first embedded system for a vehicle was released. The Volkswagen 1600 used a microprocessor to control its electronic fuel injection system. Let us now move on to the embedded system hardware, and part of this are the microprocessor based and microcontroller based. Embedded system hardware can be microprocessor or microcontroller based. In either case, an integrated circuit is the heart of the product that is generally designed to carry out computation for real-time operations. Microprocessors are visually indistinguishable from microcontrollers, but while the microprocessor only implements a central processing unit and thus requires the addition of other components such as memory chips, microcontrollers are designed as self-contained systems. Microcontrollers include not only a CPU but also memory and peripherals such as flash memory, RAM, or serial communication ports. Because microcontrollers tend to implement full, if relatively low computer power, systems, they are frequently put to use on more complex tasks. For example, microcontrollers are used in the operation of vehicles, robots, medical devices, and home appliances, among others. The higher end of the microcontroller capability, the term system on chip, or SoC, is often used, although there is no exact delineation in terms of RAM, clock speed, and so on. And for our last subtopic is the embedded firmware. The firmware on embedded systems, referred to as embedded firmware, a specific software written into the memory of a device that serves the purpose of ROM. But this can be updated more easily. Firmware can be stored in non-volatile memory devices including ROM, programmable ROM, erasable PROM, or flash memory. Embedded firmware is used to control various device and system functions. For example, telling the device how to communicate with other devices, perform specific functions, and prove input and output functionality. The delineation between the terms embedded firmware and embedded software are blurring, but embedded software often refers to the only code running on a piece of hardware, while firmware can also refer to the chip that houses a device's basic input or output system, or unified extensible firmware interface, which connects software and the system's operating system.